Okay, so this video is going to go over some things first before we get into the questions. So first we're going to go over what U substitution means and some examples, and then we'll go question by question. Okay, so first of all, what is U substitution? Well, you already know the reverse of this. So you know, for example, if I say some function, I don't know what to call it, capital S. If it's sine of x squared, the way we take the derivative of this guy is derivative of sine is cosine of whatever it is inside times the derivative of what's inside. We know this. And we can come up with more examples of this. But generically, what we're looking at is we're looking at the situation where you have a function of another function. You have an inside function and an outside function. When you take the derivative, you take the derivative of the outside function, but you just leave the inside stuff as it is, like a macro. Think of in computer science like a macro. But if you don't know what that is, it's just like a symbol. Whatever that g of x is, you leave it intact initially for stage 1. Then you disassemble it for stage 2. And this thing can go as deep as you want. I like to tell my Calc 1 students, I want you to think of if you have, okay, this is quite ridiculous and that's the whole point. I want you to assume you have some kind of snake. All right, and a snake has eaten a mouse and the mouse has eaten a fly. I don't even know if mice eat flies. It doesn't even matter, okay? So if you want to dissect the snake, first you dissect the snake, but you can't dissect the stuff that's inside until you get inside. So first you dissect the snake, and then outside the snake you put the mouse, and outside of the mouse then you put the little fly, like if you could do this. Okay, so first you'd have a disassembled snake sitting here, and there would be a big hole in the snake, and then you would have a big disassembled mouse, the big hole in the mouse where you took the fly out, and then you take the fly out and you disassemble the fly. Okay, and so similarly, if you have something like f of m of, I don't know, like b of t, like b is bug, if you want to dissect the whole thing, if you want to take the derivative of the whole thing, you have to first dissect, well, f is meaning the snake, so f prime of m of b of t, because you can't take out the bug and you can't take out the mouse until you first dissect the f, which is the snake. And then after that, outside, now that you've dissected the snake, then you can dissect the thing that was inside, but initially you can just dissect the inner part, which is m, and then finally you can dissect the inner part. So no matter how deeply it's nested, you have to attack the outside first, and then the inner layer, and then the inner layer, and work your way in until you finally have all those inner layers accounted for. Okay, so when we go in the normal direction, the derivative direction, we call this thing the chain rule, and as soon as we reverse it, we call it U substitution. And conceptually, it's exactly the same thing. You're just undoing the chain rule. But because we as humans look at it differently, we identify it differently, and we use different problem-solving techniques, often we give it a whole different name just as a way of saying, hey, we use different human tools to recognize it, but mathematically it's identical. So you're literally just undoing the chain rule. So what you need to look for is you need to look for this structure. You need to look for an outer function with an inner function inside, right? And then you see the derivative of that inner function nearby, and that gives you a clue that you can repackage everything. Okay, so what if you see something like this and you're being asked to do an integral on it? Okay, so what your eye should see is your eye should pick up on this key part and say, wait a minute, that's the derivative of that other key piece. That is what you're going to key in on. And so the way we do this is we call this key piece U, and we call this part U prime. Okay, so if we say U is equal to 3x to the 7th du equals 21x to the 6th, then what we do is we do a replacement, but I forgot the dx part. The dx has to go here. So you can write du dx over here, but we actually break up the differential, and that's a little sleight of hand. It's actually completely legal, okay? And I'm not going to go into that today, but trust me, there's a lot of deep mathematics going on. But if you just think about what it means a little piece of u is 21x to the 6th times a little piece of x. And what does that mean? Well, that means there's a conversion going on. So we're going to take this piece here, we're going to rewrite it as cosine of u, and then we're going to take these two pieces together, and that is du, and we're going to take an integral of that. And now we can go ahead and take the integral of that. Since the derivative of sine is cosine, then we've got this going on, and then we can go ahead and replace the u. And I highly recommend, this is just generic advice, but I highly recommend, especially when you're learning u substitution, as a sanity check, you take this piece that you just got as your answer and make sure that when you take the derivative, you do indeed get back to this messy expression, okay? Because if you don't, then you did something wrong. And the process of going both ways will help you debug what you did that was wrong. This brings up another important point. When you're doing u substitution, if it's a definite integral, what we just did was an indefinite integral, but if we do a definite integral, you have two paths you can take. I'm going to show you both ways you can do this. Okay, so this guy, you can say, wait, this looks like this could be a u. And then if that's u, what's to prevent du from being 6x dx? Nothing. Okay, now I'm going to convert this. So then I'm going to get u du over here. Now I have two options. I can either convert everything into u's and never go back to x's again, or I can go back to the x world. So this is how I can convert everything. So these guys are in x world. Okay, u world is I square that, multiply 3 by 3 and add 1. So square, multiply by 3 and add 1. So the new upper limit is u equals 4. And the new lower limit, okay, we were 0, and now it's just going to be 1. And so now I don't have to go back to the x world. I can say u squared over 2 must be, and this is a definite integral, so I don't need the plus c. And then I go from 4 to 1, and I go about my merry way. You can finish that. The other option is for you, instead of doing that, and this is what I would do if, this is my little shorthand. I want to remember that it's a definite integral, but I just put a squiggly here, meaning I'm not going to bother calculating it. It's some u value that I don't care about, but I'm going to convert to x's next. I'm going to say u is equal to 3x squared plus 1, and that is going to be squared over 2. And then I'm going to go back to 1 and 0. And whatever result I get is the same thing I would have gotten if I had just stopped off in the u world. Sometimes it's easier to just convert everything to your new variable, and sometimes it's easier to go back to your old variable, and it doesn't matter mathematically. It's whatever is easiest for you at the time you're calculating it. Makes absolutely no difference. There are some exercises in which one or the other will be easier on you mentally because of some of the weird conversions that go on, but for the most part it should not matter. Okay, now there are a couple important tricks that come out as a result of this stunt, and I want to show you. One of them is that now if you're just shifting something, if a function g of x is literally just shifting something like f of x plus c, you're literally just doing a shift. It's not actually going to change the variable, but it's going to change where it happens. I'm sorry, the derivative. So for example, if you had a function g of x, here's g of x, then literally f of x and g of x are only off, like they're shifted left and right. So you see, it's not actually going to change anything except where it occurs. However, that's sometimes hard to visualize. And so instead of worrying about exactly which direction it goes, we can get around the whole thing. We can use the infrastructure given to us by U substitution to completely bypass the whole mess and just crunch everything out mechanically. So let me give you an example. Okay, I'm just making this up, right? But I just really don't feel like thinking about which way that's shifting and how that's going to affect everything. I just say u is equal to x plus pi, and I use this infrastructure. Du equals dx. So this becomes u is just x plus pi. I can convert entirely into u's, or I don't have to. But anyway, I've just gotten rid of this. So I've allowed the infrastructure of the u substitution to tell me which way everything should go, and everything should follow correctly, because I'm just following the u substitution guidelines, and then everything downstream is what you're used to. Okay, and let me show you another cool trick. Okay, and the reason I keep using sine and cosine is to indicate to you that that's sort of an atomic thing. You don't have to pull it apart or do anything with it. So you have some other big fancy function. It doesn't have to be just sine or cosine. Anything that you would be able to handle on its own, but instead there's a line shoved inside of it. Well, this really, u substitution is kind of overkill for this problem, but it actually allows us to do the algebra without getting confused. You see, now du, again, it's du over dx, is equal to 3. So go ahead and put the dx over here. But notice there's no 3x up above. So what you can do is you can say, well, wait a minute, I need there to be a 3x. There's a couple different ways to deal with this, but I can just replace the dx with 1/3 du. So I just divide by 3 on both sides, because I'm going to replace this dx with 1/3 du when I do my swap out. Okay, so I replace parts for parts. It's like I'm doing a repair and I need to replace a part with an equivalent part. Okay, so sine doesn't get replaced. I'm keeping sine, but it's the 3x plus 7. I don't like that, and I'm replacing that with u. And the dx is getting replaced by du over 3. I may as well put the 1/3 over here, or if I'm feeling especially like laying it off to the side, I can put it all the way outside the integral. It's fine there too. Okay, so this is great because it allows us, again, to get away with this. And if I don't feel like converting my limits, or maybe I have an indefinite integral, okay, then that's fine. Then I'm going to just say derivative of negative cosine is sine, right? And then I always just double check this. If I try to take the derivative of sine, I'm going to get cosine. So the sign is flipped, the sign. So it's always the opposite of taking the derivative. So the integral of sine must be negative cosine. And so now I can just say, all right, that's cosine of 3x plus 7 plus c. And now I can just go ahead, take the derivative of this green function and make sure I get back to the blue function. And indeed I do. Okay, so you can take care of any function that you're used to taking care of, any function that you can normally integrate, but you have like an mx plus b inside. Now, in this u substitution gives you the algebraic tools to manage that gracefully, and you don't have to worry about getting stuck, because the algebra will do everything for you. There's something I wanted to show you. It's my little elephants that I like to show to my Calc 1 and Calc 2 students. And if we were in real life, I would have them in class. There we go. Okay, I like to call this guy Elephant, and I call this guy Elephant Prime. That's a little elephant. Okay, I got this one at the dentist. And this one, I think I got at the mall or something. Anyway, so I like to say Elephant Prime over elephant. Like the little elephant likes to climb on top of the big elephant. Okay, in real life, I snuggle them this way. But I like to do in class this elephant prime over elephant, so the baby is on top of the mom. And there you go. This is the thing I want you to remember, and I'll show you why. And while I've got my camera on, I just want to show you the snow today. This is is what passes for a blizzard in these parts. Can you even see it? I don't think you can see it. It's my neighbor's house. There we go. That's what passes for a blizzard in these parts. Yeah, you can actually just see her driveway. That's because they drove away. But there's really not that much snow. Anyway, but anyway, so there's my little elephants, and then I'll tell you what this is all about in just a second. Okay, so if you want the derivative of natural log of f, if you remember, the derivative of natural log of x should just be 1 over x. So if you want the derivative of natural log of f of x by the chain rule, the f of x goes on the bottom, and therefore the derivative goes on top. And so this is why I just replace f of x with the word elephant, just because it's silly. And somebody pointed out natural log looks like elephant somehow, but I don't know. Elephant I put in here. And so the derivative of natural log of elephant is elephant prime over elephant. Why do I do that? Because for whatever reason, when we combine natural log, which confuses people, with the chain rule, which also confuses people, we end up with elephant prime over elephant, and then a whole bunch of people just completely lose it. And that's why I was like, okay, I'm going to make up a whole separate rule for elephant prime over elephant, because people get confused when we take two rules that confuse people and combine them. It confuses even more people. So it's just why I just gave it its own special rule. Elephant prime over elephant is just what happens when you put an elephant inside natural log of x. Natural log, that's it. That's what elephant prime over elephant means to me. And so when you see these exercises for students, okay, here's just an example. It's elephant prime over elephant. So you know, without even doing it, like it's just perfectly elephant prime over elephant. The answer is just going to be natural log of elephant. Right? You don't even have to worry about it. So because you've just kind of memorized that as something to look for, something to be aware of, that's a combined rule. You're combining the chain rule with the natural log derivative, and so you end up with an elephant prime over elephant, and then just recognize that. That's all. Just recognize that as a whole separate type of question, and it's like a get out of jail free card. So you have things like e to the x plus 7 over e to the x. It looks really, really scary. It's just elephant prime over elephant. So you're like, wait a minute, that's just elephant prime over elephant, so the answer must look like this, and it just saves you a lot of grief. Okay, I guess I lied to you when I said I was going to talk about the questions, because now that I'm looking at the questions, everything I just said is sufficient to get you through the questions. So you shouldn't need any more hints. I will say this, though, that as you go through doing U substitution, you will become more adept at it, and there are often questions where you can use more than one thing to do the U substitution. So like if you get something like this, and you might ask the question, what kind of U substitution can get you out of this mess? Well, this guy could be the U, and that would work, or this whole thing could be the U, and that would get you out too. So when you use U substitution, it's not necessarily a unique U. There are some creative problems where there may be 3 different types of things that you could siphon off and say, well, this could be U, and this will work. So just be aware of that. It's not always cut and dry. There's often more than one path to a correct answer. All right, so enjoy that, and I will see you in class. Have fun.